We'll cover the other part, that is area through approximation, and first we'll cover 2D and then we'll cover 3D. So 2D and 3D. What is area under with approximation? So whatever we have discussed till now is that addition has many forms, and one form if we add something, then other form is if we multiply it, and third form is that addition can be achieved through calculating the area. So if I have a time, I have a x-axis at time. So first is 1 hour, 2 hour, 3 hour, 4 hour, 5 hour. If this is the time, then I have rate of collection of the kilometer per hour per unit of time per hour. If I know that, like, rate of collection means a person is walking at constant speed in a way that every hour he is collecting 2 kilometers. Okay, so if I see the collection per hour graph, then it is constant 2 kilometer per hour. Every hour, so if every hour he is collecting 2 kilometer, at the end of 5 hours, he is collecting 10 kilometer. So 2 into 5 is 10. But if 2 is vertical and 5 is horizontal, 2 into 5 becomes the area of the rectangle. So if I calculate the area of the rectangle, then we calculate the addition. 2 into 2, 2 plus 2 plus 2 plus 2 plus 2, 5 times 2 into 5, or area of the rectangle. But it comes into the picture that if suppose the collection of the kilometer per hour is not the smooth, it's not constant, it is like this, okay, or it is like this. So this is x square. So if this is t, if this is t, then it is t square. Okay. So at 1 hour instant, the collection per hour at that time it is 1. Okay. Earlier, if it is time and this is the collection per hour, then at every moment the collection per hour is constant. That is 2 kilometer per hour. If this is the time, then collection per hour, if it is t square, then collection at time 1, 1, 2, 4, 4, 3, 9, 4, 6, 16, and 5, 25. So that is t square. Now, if I want to calculate the collection at the end of 5, then I have to calculate the area under it. So that area calculation I don't know. So I know the area of the rectangle. So what I can do is that I can take any place the height and width, and I'll calculate and say it is the area. So at the end, if I take that is 5, at the end it is at 5, the height is 25. So 25 is height and 5 is the width, then it will come as 125. So 125 is the area. This is my answer. If I go with the t square function area through integration, if I know, then it is t to the power 3 by 3. So t to the power 3 means 5 into 3 power 3, 125 by 3. That will come around 41 point something. Let's consider 42. It will come as 42. So at the beginning, if I took the end height and width, it came as 125. So 125 area is far away from the 42. So what is the area if it is t square? Okay, how we calculate the accurate area? I know the rectangle area. So rectangle, if I take end height and width, then it is not good. So I can chop it so that rectangle will be more accurate. This is approximation. So at the end of 1 hour, it is height is 1. So 1 into 1, 1. At the end of 2 hours, okay, so height is 4. 4 into 1, 4. At the end of 3, 9, 16, and 25. So 25 plus 16 plus 9 plus 4 plus 3 plus 1. Let's calculate. So 1 plus 2 is 3, 3 plus 1 plus 4 is 5, 4 plus 9, 9 plus 5 is 14, and then 16 plus 14 is 30, and then 25 plus 30. Okay, so 25 plus 30 is 55. So now earlier we calculated 125 as area. Now area is 55, very near to 42. So this proves that if I make a small rectangle, if I chop it into, now I chopped it into 5 parts, and in 5 parts at the end we took the height, and whatever the rectangle come, we calculated the area. If I chop it into n part where n is infinity, then we approximate we can level the kind of the area. So if I take only one part and calculate the end height into width, the rectangle area is far away from the actual calculation. If I put it to 5 parts, then I have 5 rectangles to calculate, and then rectangle area is near to the actual rectangle. So irrespective of the equation of the line, irrespective of the equation on the line, I can chop it into so many parts. Now, in each part, I can take any ft. So, if this is t and this is ft, so in each rectangular portion, okay, so if ft is going through, in that region, I take any point as ft, either entry point or exit point or center point. Ft, if I take that height into whatever the width, so suppose the width is delta t, the width is delta t. So if it is first, second, third, fourth chop, then ith chop, then height would be fti or fi denominator like down, and then subscript, and then T, FIT into delta T, because delta T is a constant width, and height at that, because it is a ith chop, first chop, second chop, third chop, ith chop. So ith chop means IFIT. For that, the FT is FIT. So FIT into delta T, the area of that chop rectangle. If that is the case, there are n chop I have made, then I have to sum it. So summation I equal to 1 to n, where FIT delta T. Okay, this way we can approximate the area as near to the actual area. So this is called getting the area of uh, any graph with respect to rectangle one. If I know the area of rectangle, then I divide into so many rectangles, and each rectangle's area we calculate and we sum it. Where so many, the count is infinity. So the width by height, so width is delta t, that is limiting to 0. Okay, so that is the scenario here. Okay, this is 2D in a sense that if this is independent component and this is dependent component, the independent and dependent they come is 2D circle. What about 3D, where independent components are in xy plane? So if it is x and if it is y, okay, so it is x and it is y, okay. Now the function over fx, so fxy, earlier we had ft, now we have two independent variables, x and y. So fxy, so fxy, if it is t, then ft is vertical, that is, if it is x-axis, that is y-axis. If x is horizontal, y is horizontal, so our xy everywhere is in this plane, fxy is vertical. Okay, so now x is horizontal, y is horizontal, then fxy is vertical. So z equal to fxy equal to some equation, some function over x comma y, fxy. So if it is independent is x, independent is y, then for every xy on this plane, there is z vertically. Okay, if that is the case, if that is the z vertically, okay, like this is the, okay, this is the 3D, okay, this is 3D. So the 3D value, okay, so 3D value at each xy there is a vertical. So vertical would vary and it makes a tool. Okay, it's make a stool because this is how Z would vary everywhere. Z can vary like a cone also. So we have cone. So cone would go like this. Okay, so okay, so like we have a cone. Okay, so we have a we have a cone. Now we have a cone. So cone, if we see, then at any point x comma y, if I have the cone, then at any x comma y there is a height. Here height is less, here height is more. Okay, so z is fxy function over xy, where xy is any point on the xy plane where x axis and y axis both they represent independent components. Now earlier we calculated the area, now we calculate the volume. This is so integration, when integral calculus, when it comes in 2D, then it is calculation of the area. That is the way we calculate the addition. Now if integration is for 3D, then we calculate the volume. This is how we calculate the addition. Okay, so now suppose that now earlier we chopped, remember that we chopped x axis into many sections. Now I chop x axis into many sections. I chop y axis into many sections. So each section I represent it as I. Each section I represent it as j. Now we have so many small rectangles. Here it is chopped like this, x direction. In y direction, it is chopped like this, so many. So it will form so many rectangles. The count of rectangle is, if it is chopped n times along x axis, it is chopped m times, n m. Along y axis, the number of rectangles are n into m. Okay, so in that case, now if I have a 3D, then at each, okay, 3D, then at each x comma y there is a z value as per the equation of the graph. So for each x comma y there is a z value. Now idea is how we can calculate the volume. If I need to calculate the volume of the, what I can do, I'll go the end of the x axis. Suppose I'm calculating the volume where x end is 3 and y end is 4, whatever comes in between. So if I have a cone, okay, so if I have a cone and if this is the center here, so from center the cone is exists. So x3 and y4, whatever the cone part come in between, that volume I want to calculate. Or if I have this stool and it is sitting on xy plane, then okay, then the whatever the height we are seeing, that is the fxy. If that is the case, then from 0 to 3 in x direction, 0 to 4 in y direction, whatever the rectangle we are getting, that rectangle maps to z value. That volume I need to calculate. So volume is nothing but height by area. Area is height by width. Volume is height by area. Okay. Now what I'll do is height. Suppose that height I'll take at the end point. The end point is 3 in x direction, in y direction 4. So 3 comma 4. Suppose it is a cone. So cone equation is fxy equal to x square plus y square square. That will come as 3 square plus 4 square square. That will come as 5. Luckily, I never thought it will come as a whole number. It will come as integer. So 5. So the height at 3 comma 4 is 5. So 5 into area, that is 3 into 4 into 5. That is the volume, I would say, but that is not correct because cone is like this, it will go like this. So at any point I calculate the height and multiply by area, that will not be the appropriate one. Every x, y, the z is different. At every xy, I took xy at the end point, that is 3 comma 4, and at that point I calculated the z and z into 3 into 4. So in approximation, the 3 and 4 I have to divide into n into m part. I can divide into 1 3 into 4. So in x direction 1 1 1 3 parts, y direction 1 1 1 4 parts. Now at each part, now I have 12 rectangles. So if suppose that if this is the rectangle, okay, suppose that I'm drawing it, this is the rectangle, this is the rectangle. Then each rectangle is one corner, whatever is the fxy, that value I'll take as the height. Then height into the area. So height into the base area. So base area, if I have divided into n part and m part, so if it is up to 3, then 3 by n is the width of one part along x direction. If I have divided into m part, then 4 by m. Or if I have divided into 3 parts along x direction, then we have taken 3 as length, then 1 is the length. In the y direction, it is 4, then 4 part I have divided, then every section is 1. So each rectangle, out of 12 rectangle we have divided, each rectangle has area of 1 into 1, that is 1. Now height we will take at the end. So first rectangle will be 1, 1. Along the x-axis, next rectangle will be 2 and 1. Third will be 3, 1. That's it. Then 1, 2, 2, 2, 3, 2. At the end, it will be 1, 4, 2, 4, 3, 4. So all the rectangles, whatever the end, right and top, whatever the end comes there, whatever the fxy value is. So what is the value at 1 1, what is the value at 1 2, what is the value at 1 3. So if I have fxy equal to x square plus y square square root, then first rectangle is the end point, the right and top end point is 1 1, that will come as the square root of 2. 1 2, that will come as the square root of 5. 1 3, that will come as the square root of 10. At the end, we have 3 comma 4. Okay, so 1 1, sorry, 1 1 2 1 3 1. Last is 3 comma 4. That will come as 5. So all the 12 rectangles, what, so first rectangle, if I go in x direction, that is a square root of 2, square root of 5, square root of 10. If I go to next rectangle, that is in x direction, y equal to 2, that is 1 2 again, 1 2, 2 2 and 3 2. So whatever the height comes, so for 3 2 height will come as 9 plus 4, 30, square root of 13. So square root of 13 into 1, because base area is 1 into 1. So first in a row where 3 rectangles are there, the area is a square root 2, a square root 5, a square root 10. Then next would be 2 1. So a square root of 5, 2 2 means square root of 8, and then 3 2, square root of 13. Like that, all the what area we have calculated for 12 rectangle, then we have to add it. This is summation approximation. So we are trying to calculate the volume by dividing into various rectangle, and each rectangle the fxy will take whatever we want. At any point we can take, at the center of that rectangle, sub rectangle, at the center we can take, at the left bottom corner, right top corner, both we take and do the average. It is up to us, whatever we want to. So we can take 4 points, 4 all corner, then average it. It is up to us. So this whatever volume we are calculating, that volume will be perfect if n tends to infinite. The number of cut we are making along x-axis, number of cut we are making y-axis, both should be infinite. So in that way, the delta x and delta y. So delta x is 3 by n, because 3 along x-axis 3 unit distance we have taken. Along y-axis we have taken 4 distance. So 4 by n, 3 by n, 4 by m, 3 by n. That is delta x and delta y. So delta x tends to 0, delta y tends to 0. Then n tends to infinity. So number of chop we are making, that should be too many. So that each chop width delta x is very less. And chop we are making along y axis should be infinite number of chop. So width along y axis for is each chop is tends to 0. So that is 4 by m. 3 by n, 4 by m. Now, the area of each rectangle is 3 by n into 4 by m. If n is 3 and 4m is 4, then it is 1 into 1. Otherwise, 3 by n into 4 by m. That is area of one rectangle. In that rectangle, we have to take any point and then calculate the height, that is fxy. So fxy into into 3 into n into 4 fxy into 3 by n into 4 by m. That is the area of one rectangle, each rectangle. Now we have to double sum it, where the I is 1 to n and j is 1 to m, or m is 1, or uh, j is 1 to m and I is 1 to n, whatever we calculate, where fxy will become fijxy. For ij rectangle, fxy into then into the delta x and delta y. So delta x and delta y are constant everywhere. I did not say delta xi and delta yj or whatever. So net is summation j equal to 1 up to m, summation I equal to 1 up to n, f ijxy delta x into delta y. So fijx is vertical and delta x delta y is the area of the subrectangle. So if I keep calculating the area and then keep adding, then full will be the approximation of the volume. So in 2D, the approximation was be cut into so many chops along x-axis, and then at each chop we calculated the ft. So fit delta t summation I equal to 1 to n. Here we chop x-axis in n and y-axis in m section, where if x-axis is 3, up to 3 we have taken, and y-axis up to m, up to 4 we have taken, then the each rectangular area will have area of 3 by n into 4 by m, whatever. The equation of the final, the calculation of any rectangle, if I take, the rectangle will be addressed as ij. Any rectangle will be addressed at ij, 1 1 1 2 1 3, like that, where I is 1 to n and j is 1 to m. Now in that rectangle, any point if I take vertical, that is z, that will come called as fijxy. Otherwise it called fxy, but at the point ij, this is fijxy. If I know at that rectangle the height, that is fijxy, and that area of the rectangle is, if I have taken 3 along x-axis and 4 along y-axis, then fijxy into 3 by n into 4 by m. So 3 by n I call it delta x, and 4 by m I call it delta y. So total number of the calculation will be along x-axis, it will be up to n, and along y-axis it is m. So sigma j equal to 1 up to m, sigma I equal to 1 up to n, then fij xy into delta x into delta y. So fij is height and delta x and delta y is the area of the rectangle. So height into area will come as the volume. So if I have 100 rectangles, then area of this 3D is approximation is better. If I have 1000, even it is better. If it is 10,000, even it is better. What is not better is I have to calculate for those many small volume. So in the 2D I called it so many small rectangles we calculated the area. Here so many small volume I have to calculate the area, where for each volume the down area is same but heights are different. Like in 2D, for each rectangle the down width is same but heights are different. So rectangle area is different. Here volume, the volume is different. So this is that analogous. This is analogous to the calculation in the 2D. So in 2D, if we know the area of rectangle through which we calculate the integration, then we divide our equation into so many rectangles, and each rectangle's area we calculate and then we add it, so that it will be final approximation to the actual area. In 3D, if the if we need to calculate the volume, and volume is height by area, then we will have so many area. I would rather say so many volumes, where the down xy is same but heights are different. So many volume will calculate, and at the end we'll add the volume to have the most nearest volume to the actual volume. So this is the approximation calculation of the volume. In last section, we talked about that if volume has an equation, fxy has an equation, then we can integrate it the way we integrated in 2D. So we will proceed more on it, but two way we have seen. One is directly through equation. So if I have equation, then we break the equation down, so that it will come to a level where I know the integration. Okay, so we talked about integrating t to the power n. So first we had t to the power 0, that is rectangle, t to the power 1, that is triangle. So from rectangle and triangle we deduce a formula called t to the power n. Integration is t to the power n plus 1 by n plus 1. Okay, so t to the power n plus 1 by n plus 1, the antiderivative is, okay, exists, and it is t to the power 9, because t to the power n plus 1 antiderivative. If t to the power n plus 1, so integration is more natural. Derivation came from integration, because addition is more natural and subtraction came from addition. So differentiation came from integration. So if integration of t to the power n equal to t to the power n plus 1 by n plus 1, then t to the power n plus 1 by n plus 1 differentiation is t to the power n. If that is the case, then differentiation of t to the power n is n t to the power n minus 1. Okay, this is how differentiation came. So the most natural is integration. So we came to formula t to the power n integration is t to the, because if we saw rectangle t to the power 0, then it became t. If triangle it is t, then it becomes t to the power 2 by 2. So for t to the power n, it is t to the power n plus by n plus 1. So two way of doing the integration. So whatever we talked now here, it is called contour way. Like we have hilly region. In hilly region, when we draw the graph on the 2D plane, then we typically we draw contours. You can check the contour. So contours talk about the height at that location. So triangular or circular, or some form of circular way, or some kind of ellipsoid way, we have the contours. So at each point we know the height. If we know the contours, then we can divide this full graph into so many rectangles, and in each rectangle one part, or will average the contours. If there are 3-4 contours, we'll average the contour and we'll come up with the some height in that rectangle. So if I know the height of the rectangle and rectangle area, then for that rectangle we can calculate the volume, so that we can add all the volume. Simple, right? Means if I have contour diagram, I can divide it into n into m rectangles, where each rectangle's area, okay, n into m. So if this width is 3 and height is 4, then each rectangular area is 3 into 4. Now if I know 3 into 4, then each rectangle we have contours. If luckily there is only one contour that is lying in that rectangle, then any point in the contour, then contour has one height. So that height into that area. If there are 4 contours, then we'll take the average of the contour in that rectangle and that height into that area. So height into 3 by n into 4 by m. Like that, all rectangles height will calculate all rectangles volume. Now volume will calculate and will add it. So that will be the net volume of the graph. So this approximation is also important when it comes as contours. But if I have equation like cone or solid or any paraboloid, then it is nice to go with the typical integration way, where if I have the formula, then divide the formula to a section where, or break the formula down the line. Like if I had triangle, then I broke it to rectangle. Okay, triangle is the area is half of the rectangle. So we came to rectangle. If I have any t to the power n, then if any equation and that is something like this, t to the power, then we will come to t to the power n stage and then we know. So if we, so this way we have calculation for e to the power x, ln, sine, cos, everything based upon this triangle and rectangle and exponents or polynomial. So if I have the equation of a graph, then I'll break down the equation to a level where I know the integration. Then we can calculate the integration the way we calculate the integration. Or if I have the contour, then whatever we talk the approximation now, that we have to use. So both way, now I know if I have a height estimate, then area into height, volume of that is the integration. So volume is height into area, that is the volume, that is the integration in 3D. Height into width, that is the area, that is the integration in 2D. So now we have got 2D and 3D approximation integration and the formula based integration. So we'll proceed on it and we will see that how the calculation of the addition through calculating the volume, it is important and how nice it is. That we'll see.